Assalamu alaikum. So we will start on lecture 4 by recalling some of the previous definitions which we have discussed in part 1 of this lecture. So in part 1 we have said that the relation R on a set S is a partial order on this set S if R is reflexive, antisymmetric, and transitive. This is how we show the reflexivity, that A is R related to A, and this is how we show antisymmetry, that if A comma B and B comma A are in R, then simply A is equals to B, and then we show the transitivity like this. Now, second definition was set S with a partial order is called a poset. And then third definition was a partially ordered set. We can write a partially ordered set like this: is linearly ordered set or a chain if for all the elements inside the set S, they are comparable to each other. Then we can say that the set is partially ordered. We have discussed a few examples for that. Okay, now let's start today's lecture with a definition. So we have a definition about the least upper bound and upper bound, and then lower bound, and then greatest lower bound. So let's talk about that. Definition 1.4.9. Let S be a set is a poset and the set which contains only A comma B be a subset of the set S. Now, an element C inside the set S is called an upper bound of this subset of S if condition is A is less than or equal to C and B is less than or equal to C. Similarly, an element D of the set S is called the least upper bound which we call LUB of the set A comma B if 1 D is an upper bound of A comma B, means A is less than B and B is less than D. A is less than D and B is less than D. 2, C, if C is an S, is an upper bound of A comma B, C is an S as an upper bound of the set then D should also be less than or equal to C. This is the definition for upper bound and least upper bound. The condition for the upper bound is this, and then for the condition for the least upper bound is there should be another element which should be also less than or equal to C. Okay, then we have example. Now let's consider the set. And together with the divisibility relation that A divides B for all A comma B in N, which we have discussed in previous example. So now for subset 4 comma 6, for the subset 4 comma 6, 12, 24, 36 are all upper bounds of the set. However, 12 is the least upper bound of the set 4 comma 6. Similarly, number 2, we have a set S which contains the elements 1, 2, 3, 4. This denotes the set inclusion relation then the power set of S with this inclusion relation is a partially ordered set. As a poset, let A is 1 comma 2 is a subset of the set S, and then B is also a subset which has 1 comma 4, elements, then their union, is just 1, 2, 4 is the least upper bound of the set A, B, a set which contains both. Some remark. One. In a poset, a subset A comma B of the set S may not have an upper bound. Two, in this poset, a subset A comma B of S may have more than one upper bound. Three, in this poset, the subset of S may not have a least upper bound. But if it has a least upper bound, then this least upper bound is unique. Perfect. For notation, for the notation purpose, write that the least upper bound of the set of the subset of the set S in a poset, if it exists, is denoted by this symbol. It means A or B, and then this means that it has a least upper bound. Okay. Then we have a definition. 1.4.12. It says that we have a partially ordered set poset, and we have a subset of S, an element C of S is called a lower bound of A comma B of this set A comma B, which can we have C is less than or equal to A and C is less than or equal to B. And an element D of this set S is called greatest lower bound which we call GLB of this set A comma B if 1 D is lower bound, which means D is less than or equal to A and D is less than or equal to B. And number 2, if C is an S is a lower bound of A, this subset of S, A comma B, then C is also less than or equal to D. And then this remark we call star is also kind of valid for the greatest lower bound. So you can say again, remark 1 in a poset a subset A comma B of the set S may not have a lower bound, but if it has, then it may have more than one lower bounds. 2, in a poset a subset A comma B of S may not have a greatest lower bound, but if it has, then it must be a unique greatest lower bound. Perfect. The notation for the greatest lower bound, so I should write this. This is for LUP and this is for GLB the GLB of greatest lower bound of this set A comma B is a subset of S in this poset if it exists is denoted by A and B. So we need to remember that. Now, a useful device in the study of partially ordered sets is actually a poset diagram. And to draw that diagram, we need to learn one more concept, which is actually covers, how two numbers cover each other. So to define that, let's say the definition again, let S this be a poset and X comma Y are elements of this S. We say that Y covers X, denoted by this is a bit tricky sign. Let's try again. Yeah, the sign. If X is less than Y or equal to Y and X is not equal to Y. And there are no other elements. And there are no elements inside S such that X is less than Z, less than or equal to Z, and Z is less than or equal to Y, comma X is not Z, comma Z is not Y. Now, let's define this concept by a definition, by an example, sorry. So let's consider a set 1, 2, 3. We have a power set which contains 5, 1, 2, 3, 1, 2, 1, 3, and 2, 3. And this S itself. Then this power set along with the inclusion property is a poset. Inclusion relation, the diagram for this inclusion relation will be denoted like this. S. One, 2, 1, 3, 2, 3. Then 1, 2, 3. So you can say 1 goes to here, then 2 goes here, then 1 goes here, 3 goes here, 2 goes here, 3 goes here. And then in the end, we have 5. And everything just connects to 5. Like this. This is a POSIT diagram for the above partially ordered set. Then we have a definition. About the maximal elements. So let's define that. Let is be a POSIT and element U in S is called a maximal or minimal element of S if there is no element V inside S such that U is less than or equal to V and V is less than or equal to U and U is not equals to V. So we have a condition maximal. And for the maximality, we have a condition that U is less than or equal to V. We have a condition minimal element. We have a minimal element. For that, we have V is less than or equal to U. And along with these two conditions, we have this. We have to make sure they are not equal. Perfect. Example. Example says we have a set and T be the set of all proper non-empty subsets of S. T be the set of all proper non-empty subsets of S. Now, T along with this inclusion relation is a POSIT. Now, in this POSIT, the subset 1 of S, 2 and 3 are minimal elements and the subsets 1, 2, 1, 3 and 2, 3 are maximal elements. This is the criteria. We'll present a very famous lemma and then we will end this part of the lecture. So let's define that lemma, which is known as Zorn's lemma. if every chain in a posset this has an bound in S. If every chain in a posset has an upper bound in S, then S contains a maximal element. Now, we'll end this part here.